Hi, I'm Dave Israel from the NASA Goddard Space Flight Center. I am our Exploration and Space Communications Projects Division Architect and also the Principal Investigator for the Laser Communications Relay Demonstration. And today I'll be talking to you about NASA's laser communications future. So we've been working on laser communications to improve the amount of data that we can get back from all of our destinations from low Earth orbit all the way out to interplanetary exploration. And the main reason that we're looking to lasers is because we've been using radio waves or RF for radio frequency since the beginning of space exploration, and that's served us very well, except there's physical limits to how much data we can actually transmit using RF technology. And the way for us to get the higher data rates is through the use of laser communications, or sometimes referred to as optical communications. Go to the next slide, please. So the benefit of laser communications is because we're operating at much smaller wavelengths, or you think of it as higher frequencies, then that brings the benefit that because of the way the physics works, then your power when you get transmitted gets focused into narrower beams, laser beams, and so you're delivering a lot more of the power that you're transmitting onto your specific target, and the ability to get more power to your target allows us to transmit and receive higher data rates because the signal to noise ratio turns out to be better. And then if you combine that with the higher frequency, allows us to modulate the signals with a higher rate of transitions, then it also gives us that higher data rate. So those two things combined gives us the ability to get a couple of orders of magnitude of data rate or data volume transmitted, and it also allows us at a same data rate to reduce what we call the swap, the size, weight, and power of our equipment on both ends of the link, which is also very important. So combining those two together is really going to be what enables our communications in the future, in the same way that the switch to using fiber optics for telecommunications on the ground, well, here on Earth, terrestrial fibers has allowed the high speeds of the internet backbone that we have. What we're really doing is putting in these fiber lines in space, except we can't use the fibers, so that's why we're doing the free space optical. Go to the next. Okay, so this video is the laser communications relay demonstration. What you saw, that first glimpse, was the hardware, the modems and the pieces of the space terminal. And here on the bottom, what you see are the two optical telescopes, or optical modules, we call them. And what LCRD has is two optical communications links. They both operate bidirectionally, meaning they can transmit and receive. And that hardware that you also saw on the spacecraft then routes the data or switches the data between the two terminals. So it allows the data to be relayed from one optical link to the other optical link in one direction and then in the other direction at the same time. So LCRD is a payload that's on board the STP-SAT-6 spacecraft located in geosynchronous orbit. And it's in a location where it can see our two ground stations. One is in Haleakala, Hawaii, and the other is in Table Mountain, California. And so as you see in the video playing in the background, the link is established between the two ground stations, and then we can demonstrate the ability to relay data from one link to the other. Now, in the beginning of our mission, our targets to communicate, the endpoints that we're communicating with, are the two ground stations, but our system is designed in order to be able to track something in low Earth orbit. So the long range idea is that one of these telescopes will be tracking something in orbit while the other one is pointed down to the Earth, and that's how we get the relay to get data between a user in space to and from Earth. So if we go to the next slide, please. So LCRD is, you see this is not the artist's concept picture, but this is an actual picture from the period of time when the spacecraft was being integrated at the Northrop Grumman facility in Northern Virginia. You see towards the top are our two optical telescopes, and you see the full spacecraft. The payload itself, it's described as being all those mounted pieces about the size of a king size bed is what we usually say. So it's on STP Sat 6. The STP is the Satellite Test or Space Test Program. That's part of the U.S. Space Force, and we are a payload on board that spacecraft. We have partners on the LCRD mission. I have co-investigators besides from NASA, but also from MIT Lincoln Laboratory that's been a long-term partner in laser communications, as well as NASA's JPL, also partners in laser comm, and JPL is also responsible for one of the ground stations, the one in Table Mountain, California. So the Space Force is giving us our ride on STP Sat 6, and ULA is our launch vehicle, and Northrop Grumman is who built the spacecraft and integrated and tested it. Next slide, please. So once LCRD is on orbit, the idea is that this is a demonstration mission. We have 2 years at the geolocation, and our whole purpose is to really learn how to operate laser communications links. We've had half a century, more than half a century of experience of how to transmit and receive data to and from space with RF links, and there's lots of things that we design into our links and the way that we operate that we've learned over time and experience that we just sort of naturally do now. There's been multiple generations that have come into the business, and there's some of those things that are just part of the way we go about our life, and maybe we don't even know what the hard lessons were that led to the design to be that way. So we don't have any of that experience with laser communications, and though there are now some operational systems using laser comm in space, those are focused more on space-to-space links. So the missing experience is mainly in transmitting and receiving laser communications links from space through the Earth's atmosphere and the weather down to Earth ground stations. So we'll be spending a lot of time characterizing and modeling those effects and figuring out the best way to operate with those situations, but also to take the system and configure it in a way where it is emulating a certain operations scenario, so that we can demonstrate how the laser communications relay will fit into a situation like a relay for exploration at the moon, or just a relay for from deep space location, or a relay in geo for LEO users. So we can configure the system and simulators that we have at our ground stations to emulate different situations. And there is something we call the LCRD Experimenters Program, or Guest Experimenters Program. There's the link that's available. You can find a document right online that's called the Introduction to Experimenters, and that document gives an overview of the mission, but also explains the types of experiments that we'll be able to run. And our goal is to not just run experiments that are applicable to our NASA objectives, but also to configure the system to help encourage the infusion of this technology into commercial systems, support any other research that might be going on to really build up this knowledge base so that everybody can get the full advantage of this new technology. Go to the next slide, please. So LCRD is part of NASA's program in implementing and infusing the optical communications technology. LLCD flew in 2013. That was the Lunar Laser Communications demonstration. This was really the big technology demonstration. This is the thing that proved that we really could build and operate and successfully transmit data using free space optical communications. And in that case, it was from the moon, 622 megabits from the moon and 20 megabits to the moon. With immediate acquisition, it performed incredibly well, improved the technology. By design, the LLCD was hosted on the LCRD spacecraft. Uh-oh. Yep, I had a momentary network dropout there. So LLCD was hosted on the LCRD spacecraft, which was the Lunar Atmosphere and Dust Experiment. So at the end of their experiment, by design, the spacecraft was deorbited and essentially crashed into the moon as part of the experiment. So our time to do our optical demonstrations was limited by that. So though we got a lot of great experience and great data, it was not a long-term opportunity. So LCRD now builds upon that experience, and we'll get those 2 years of experience. The technology that was all designed and integrated by MIT Lincoln Laboratory for LLCD has been transferred both to industry and some to NASA. So the LCRD was also the first time that these technologies were a lot of the components were all procured from industry, with some efforts like the modems being built by NASA. But this movement from a specialized MIT Lincoln Lab to industry is part of what LCRD has been about, and that's what's been happening in this time in between. So LCRD gets on orbit, and then in soon thereafter in 2022, the Illuma-T terminal will fly on the International Space Station. That will provide the space station the ability to close optical links with LCRD itself. So this gives LCRD an orbiting user to demonstrate and test with, and it also gives the space station first the capability of demonstrating what it would be like to have a user optical terminal on a LEO spacecraft, and then our goal is to evolve it to the point where we are supporting some operational data flows to and from the space station through the Illuma-T terminal and LCRD. Also in the 22 timeframe is a mission that we call T-Bird. This is a small set that's going to fly in low Earth orbit, and it's actually going to demonstrate 100 to 200 gigabits per second directly from low Earth orbit to the Earth. And this is potentially a huge game changer just for the whole way that we operate and the way essentially things like Earth observation missions can collect data, fly over top of a university or principal investigator or somebody's ground station, which could be a small telescope on the roof of their building or in their parking lot, and dump a whole day's worth of data just straight to the user's location. So that we call a T-Bird. And also launching in 22 is the Psyche mission, and that's got the Deep Space Optical Communications terminal being developed out of JPL, and that's going to the Psyche asteroid. So this will be demonstrating all of the additional complexities that deep space links bring. And then in support of human spaceflight, when Artemis 2 flies, then we have a payload on there that we call O2O, that optical to Orion. That will be the path for all of the high definition videos that we're all looking forward to seeing when the astronauts first go in the vicinity of the moon. The Artemis 2 mission is the mission where there'll be astronauts on board. They won't go onto the moon surface yet, but they're going to orbit around the moon and be sending back HD video, and the optical link will be the way that we're able to get that bandwidth that will allow us to all see those pictures. So go to next, please. Okay, so as I mentioned in the very beginning, one of the important driving needs for laser comm is that when we go to these farther distances, like Mars for exploration, then it really becomes just impractical to use RF links to get the data rates that we know that are going to be necessary to do the science and exploration that we want. So LCRD, though it's only going to be in geosynchronous orbit, will really help us towards these end goals of the planetary laser comm, because we're only in geo, but we're above the Earth's atmosphere and the weather. So everything that we need to learn and understand about the issues of dealing with the atmosphere and the weather, we'll be able to do with LCRD, and also the ops concepts that we want to demonstrate, such as networking, delay disruption tolerant networking, DTN, for example, how to interact with the human spaceflight missions once we bring in ISS and Illuma-T. All of these things will allow LCRD to test out and be a proving ground for those future applications, including on the next slide. When we go to the moon soon, and we're working on something that we call Lunarnet. So the optical links in the Lunarnet, if you think about here on Earth, where we have the transatlantic fiber cables to provide that intercontinental connection between North America and Europe, to aggregate a lot of the traffic that's going between the continents, pull it all together to a single communications connection, and transmit it between continents over a fiber optic cable, then that's really the way to view where the laser comm will fit in for Lunarnet. There may be some users that need the higher bandwidth, that just their own data would be on an optical link to and from the moon. But another use case is to have a relay in the lunar orbit or lunar vicinity that is the same as that transatlantic fiber provider, but instead of being an intercontinental connection, it's an interplanetary connection, or a connection between the moon and the Earth. So what you'll have is a lot of the user data will go to a relay, and maybe that relay will send the data back to and distribute it through locations on the moon, but some of that data is going to want to come back to Earth, and all that data would get put on, instead of onto a fiber cable, then it will be put onto a free space optical link and sent back to Earth, and then vice versa in the other direction. So that's how the optical comm fits into our future plans for Lunarnet. So I believe that's the last slide. So there's some links here available that has a lot of information about LCRD and optical communications. There's a lot of STEM lesson plans and activities for people of all ages and information. So please, I encourage you to explore the links. And I believe I'm finished. Thank you.